Okay, in the last video, I discussed filter methods. Let me show you the slide of filter methods. Here is the slide of filter methods, and here is the slide of wrapper methods. So I'm going to discuss wrapper methods in this video. But before, I want to switch back and forth to filter method and wrapper method. What's the difference? What's the difference you're seeing? This is wrapper method. This is filter method. This is wrapper method. What's the difference? As I mentioned earlier in the previous video, in wrapper methods, there is certain criteria here that is machine learning model independent. This criteria, whatever that criteria is. There are different criteria that we will discuss later on, but there is some criteria that you focus on. In wrapper methods, you actually have a machine learning model to guide you select different features. The rest of the story is mostly the same. You have the subset generator that actually search the subset of features, and once you find a best subset, you actually output the best subset. But here you rather than relying on a criteria that is machine learning model independent, you may have some criteria to help machine learning to help selection of these features. Let me explain this with an example. Let's say you have features, let's say x1, x2, x3, ... let's say xd. And again, let's say this is a supervised paradigm. Let's say you have a target label y. Let's say it's a classification task. And you are aiming to fit support vector machines, let's say that's a classifier you're aiming to fit on this particular data. You're aiming to apply this machine learning model on the data. So what you will do is the following. First of all, you will be having a lot of training data. So you will be having record 1, you'll be having record 2, you'll be having record 3, you'll be having a lot of training data. So if I think about this training data as the following, that's all the records. This is record number 1, this is record number n. Let's say that's all your data that is available. So each data is basically d plus 1 numbers, where d numbers are the feature values and 1 additional number is the class label. So 1 point consists of d plus 1 values. If your training data, if this is the amount of the training data, then what you can do is in wrapper methods, what you can do is you can hold out a particular portion of the data, maybe 20% or 15% or some percentage of the data, maybe, and that is called sometimes the holdout set, also sometimes called a validation set, and there are several other names, holdout set. And you pretend that this holdout set, it was never available, and it is not available. I mean, you just hide that data somewhere. It is not available. Just pretend it is not available. And this is the data that is all available to you. So basically, that's the portion of the data that is available to you. Let me call that data as new training data or training data. So you pick let's say 80% of the data, and that's your training data, and you just hide, let's say 20% of the data, which is holdout data. Now what you do is on training data, you select a particular subset, and on that subset, for example, you select a subset of, let's say x1, x4, x35. Let's say you select a subset of size 3. So what you do is, that subset is given here. What you do is, in your training data, you just pick x1 values, x3 values, and x35 values, so that the data is 3-dimensional. Your feature space is 3-dimensional after selection. Now on these features x1, x3, and x35, you from the training data, you train your model, let's say SVM. You train your model. After training the model, you pick the holdout set. and you test the performance of your model on this holdout set which was not used in the training process. If on this holdout set the performance of the model is great, then the best features are X1, X4, and X35. If on this holdout set, which was not used in the training process initially, if the performance of your model is not that great, then you may think that X1, X4, and X35, that subset is not a great subset, and then you refer back again to get another subset. Another subset is given, the model is trained again, and you test the performance of the model on a holdout set, and you keep on repeating this process until you get a subset that is the best. These are called wrapper methods, and they specifically require a machine learning model upon which you basically so rather than a criteria here, you have a machine learning model to guide the search. The problem is with wrapper methods, they are sometimes really slow and time expensive because training of several machine learning models, several of those is really a time-taking task. And if we have to generate a lot of subsets, and for each subset we have to retrain the model. And if the training process is really slow, which mostly is the case for a lot of machine learning models, then selecting the best subset requires a lot of trainings of the model on different subsets, which is sometimes very, very expensive in time and takes a lot of time. In contrast, the filter methods are sometimes fast. They do not need a lot of retrainings of a particular model. The criteria is somewhat, in most of the cases, this criteria is somewhat very easy to compute. It does not take as much time as machine learning training, as the training time of a particular machine learning model. So these wrapper methods, they are sometimes really slow and should be avoided if this particular model, if the training of the model is really time expensive. But on the other hand, these wrapper methods, they actually give a more accurate description of more accurate selection with respect to the model. If eventually you are planning to use SVM, then why don't you let SVM guide which features are good? In contrast, in filter methods, there is no criteria. There is no machine learning model that is guiding. Wrapper method, however, give a true the expectation of the true performance on an unseen data when we are going to deploy a particular model. So if you have anticipated a particular model that you're going to fit, or a set of models that you're going to fit, then this selection process actually get help from that model, and the performance on your holdout set basically gives a true estimation or a true indicator of what will be the generalization when these selected features, they will be, when this particular model, SVM or some other model, it will be trained on the selected features. So wrapper methods, although it has benefits, it gives a better indication, true indicator of, better indicator of the generalization performance given a particular model. But the drawback of these wrapper methods is it's expensive, it's slow because it needs a lot of trainings of the model, and the training of the model is sometimes really expensive. So now that we have gone through a filter method in Python using scikit-learn, let's implement a wrapper method. So yeah, so let's implement a wrapper method based on search strategy, which is recursive feature elimination. So here, let me just give the headings here. Yeah, so here I can give the heading. Where's the markdown? Heading. Filter. Filters. Filter. So, yeah, so that's filter. So now I'm going to give a heading here for wrapper. So let's have a wrapper. So these are the wrapper methods. Remember, we already have computed this x new, which is 5,000 and so on. Okay. So for wrapper, let's select, remember for wrapper, we have to first select a machine learning model. So let's select a particular model, maybe logistic regression, or maybe support vector machines, or maybe random forests. There are so many models. Select one of those or several of those and get the voting at the end. So let's select one of those, logistic regression. That is faster. So scikit-learn dot linear model import logistic regression. Yeah, import that. So that's the model we will be using. You can import another model, for example, from scikit-learn dot svm, for example, import linear svc if you really want. Yeah. So you can use this one. You can use a support vector machine. You can use a random forest classifier, or any one of those. Let's say for this particular task, we are using logistic regression. So even if you replace this logistic regression with this linear SVC, the rest of the story will stay the same. So that's the model that will guide us to select different features. Now we have to specify the search strategy. So let's have the search strategy as scikit-learn dot feature selection. From this, import search strategy as recursive feature elimination. Yeah. So we can have recursive feature elimination, and equivalently, we can have recursive feature elimination with cross-validation. So that is also there. So if we have CB, if we have recursive feature elimination cross-validation, if we import that, that helps us eliminate the features using cross-validation. Cross-validation is a concept that the data is divided in a way that the different portions of the data, they act as well as training as well as testing in different iterations of the validation. So for example, the first 90% of the, let's say the data is in a particular order, and the first 90% of the data act as a training, and the last 10% of the data acts as a validation set. So that will compute some best features, whatever those are, and stuff like so. But then next time you repeat the iteration by keeping a different 10% as a holdout set or a validation set, and a different 90% to be the training set. And then you repeat this process. So for example, a 5-fold cross-validation actually makes a five partitions of the data, where one partition acts as validation and the rest acts as the training data combined way. So this cross-validation is there. One benefit of this cross-validation is that if you apply recursive feature elimination using cross-validation, you need not to supply how many features you are going to select. It will select the best number of features automatically through cross-validation. But at the cost of time, because this cross-validation is expensive, so it will take a lot of time to do that. So we will be using recursive feature elimination. I will also be writing these RFE wherever I use this, just in incremented form if you want to do that, if you want to use that. So we have imported these feature methods for logistic regression and RFE. Next, we build our model. Let's say our model is, let's say, logistic regression model. Let's say that's our model. If you really want to use linear SVC, this model or some other model, all you have to do is to write m is equal to linear SVC and the parameters that it requires. Here you can give the parameters, or if you really want to rely on default parameters, you can go with that. Yeah. So that is our model. Now, you also have to set the search strategy, and in the search strategy, you have to give the model as well as the total number of features that you really want. So here I want, for example, 200 features. I want the recursive feature elimination to move down to 200 features. If you really want to apply a cross-validated version of that, you can write S equals recursive feature elimination with cross-validation model, and here you have to specify the total number of partitions for the cross-validation. For example, 5-fold cross-validation. Here you need not to specify the total number of features that you require, because this cross-validation automatically selects the best number of features. Here you have specified that I need 200 features, no more than that, no less than that. So yeah, after that, what you have to do is you have to actually apply a transform. So that's a T equals S dot fit X Y. Yeah, great. So what is going to happen is really terrible, because this recursive feature elimination is going to happen on 2401 features in a recursive fashion. So as I explained in my slides, it will, although the classifier that you have selected is really fast, it's a linear classifier, really fast, logistic regression, but this recursive feature elimination requires a lot of trainings of this logistic regression, and it will take a lot of time. I will wait for a few seconds for you, and then I will interrupt it, because it may take several minutes or maybe hours. So for example, it is working now. So this star means it is still working. If you wait for a couple of minutes, maybe 15, 10, 30 minutes, maybe 40 minutes, depends upon your machine as well. The expectation is it will still be running. So what I can do is I can interrupt it. I can interrupt the kernel because it is taking a lot of time. Instead, what I can think, why don't I use xnew? I already have reduced the dimensions using a filter method, and the dimensions are already to 500. Now, using the original dimensions 2401, that may be very time consuming. Why don't I use first a filter method to filter irrelevant features, and then use a wrapper method based on the result of the filter method? That may be faster. So let me use, for example, rather than this, let me use the following. So I'm going to use the following. So T is s.fit on x new, which is already filtered out by a filter method, only have 500 dimensions. And now I need 200. Now I need recursive feature elimination on logistic regression model, and I want 200 best features. So let's run it. What is going to happen, it is still going to take a lot of time. And that's precisely the reason I told you that the wrapper methods, they are slow. For large amount of data, when you have a lot of data with a lot of features, the search strategy, recursive feature elimination or forward selection, it requires a lot of retrainings of your model. Even if your model is trained a little bit quickly, the total number of retrainings are so large that it is going to take a lot of time. So yeah, so I'm again going to interrupt this. Yeah, bad. What I've done already is, for you, I have already trained this offline, and I have saved the result in T in some file, and now I'm going to load that file just like this is available. So I'm going to load that file. For example, import pickle. When I use this command to compute T. It took several minutes. Then I saved that here using this command, pickle dot dump. What variable I really want to save in a file to use later on. That variable is T here. This T on xnew, and what I really I have to set the name of the file, any name. I have set t.p, and then I have to set that I really want it in a writing mode. So that I called earlier offline. and it has saved the file. It has already saved the file. What I'm now going to do is I'm going to load that file. So to load that file, I will say, okay, t equals pickle dot load, and I will give the name of the file that I have already saved for you. That is t.p, and I want to open that in read mode. So read mode, yeah. So yeah, I've already done that. If really I want to wait for this training to happen, this video will become lengthier and lengthier, and we will be doing nothing just by waiting when this call will return. And if you call this one, then forget about that it is going to return very quickly. So what I did is I called this function earlier and saved the value of t somewhere just to save the time for this video. And further, think about deploying a model that is complicated than logistic regression with respect to its training time, maybe a neural network or support vector machine with a Gaussian kernel and stuff like so. That will become really, really time expensive. And that's the reason the wrapper methods, they are really time expensive. And further, the time will become further elongated if you call the recursive feature elimination using cross validation. Yeah, so that's the case. So now just think about this call has returned and we have our t here. So now that we have our t available with us, we can see the model t. It's recursive feature elimination. The model inside is logistic regression with these kind of default parameters, all of these. And the number of features we are going to select are 200. Yeah. So next, we really want to get the support, what features we actually have selected. So mask is t.get support. So, and then we just display the mask. So this mask will, the true values means that feature is selected. So this feature is selected, that feature is selected, and this feature is selected, and this feature is selected, and so on. So all these features are selected. So 200 of those. If you really want to know which features are selected, if you really want to know the indices of those, we can have, for example, np.arrange of 500. That's an NP array. And then we can apply a mask here. Hope it works. So these features are basically selected. So these are 200 features. If you just see the length of this, these are 200 features out of 500 features. Yeah. So which features are selected? These features are selected. After all, so in the first phase we apply a filter method and we reduce our dimensions from 2401 to 500 using filter criteria, which is f-classif, which is f-score. And then we apply a wrapper method on top of the filter method. So first we process data using a filter method, and then we cascade a wrapper method on top of that, and we use logistic regression model and recursive feature elimination and select the best 200 features. And now we are basically ready to go and create basically our new features. Basically we are ready to go, and just based on these 200 features we can implement our logistic regression model. One thing that you must notice is these wrapper methods, they are also correlated, or they are binded with the model that you used while feature selection. So for example, if you have used logistic regression while the feature selection phase, and then you deploy a linear support vector machine at the test, so you select features using the model logistic regression, but then on those selected features, if you run a different classifier, if you train a different classifier, then the guarantee of accuracy or the generalization may not be guaranteed. So yeah, so that's the wrapper method, and here we have selected 2000 features.